And having access to the best telescope that we were ever able to build, which is what we anticipated JWST would be, that allowed us to dream and plan and think about what we could do with this premier facility in the solar system.
We have two basic capabilities. One is take pictures, and one is stretch out the light of an object into a rainbow to see how bright is it at each different wavelength. So that's really important for us to do the chemical analysis and the physical analysis of what's in the object.
In any public talk I give about JWST, I always start by explaining what spectroscopy is, because I call it JWST's superpower. The spectra are so fabulous that when you get a group of scientists together, you show them the brand new JWST stuff, and what makes the audience gasp is a spectrum. It's so good, so clean. The lines are so beautifully resolved. The sensitivity is so exquisite that you just see molecules.
So we never get to print a picture of a spectrum in the newspaper because it's too abstract for people, but it's the thing that astronomers use to know what's going on inside those things that we find.
As a chemist, I can tell you the spectroscopy is the best part about the James Webb Space Telescope. Yes, we're getting fantastic images, but even the distant galaxies, you know, the hunt for the first galaxies of the universe, they're dependent on the spectra. The images only give you so much information, and without seeing the actual spectra, you can't confirm the distance of an object or, you know, the pristine nature of that object. I'm Stephanie Milam. I'm the JWST Deputy Project Scientist for Planetary Science. I decided to become a scientist when I was actually very young. I grew up in Houston, Texas, and I went on a field trip down to Johnson Space Center when I was about 6 years old. I came home just absolutely elated, and I told my mom, when I grow up, one day I'm going to be an astronaut, I'm going to work for NASA. Pretty much everything I've done since that moment has been to become a scientist and to work at NASA someday. I knew that I wanted, to become a mission specialist, so I needed to pursue a PhD, but at the time I was working in an environmental laboratory, basically washing glassware for a living to get myself through school. And I knew that I couldn't spend the rest of my life doing this. And I asked my advisor, how can I become a chemist and not have to deal with wet chemistry ever again? I never want to see another beaker. She knew I had a passion for astronomy, and she said, have you ever heard of something called astrochemistry? And that was sort of the turning point, and my laboratory went from, a room where I was washing beakers to now the entire universe studying chemistry of the cosmos. If you would have asked me when I was an undergrad in Kansas whether or not I would be working on the largest astrophysics mission NASA's ever had, I would have never imagined it. Never.
The way the program worked for those of us who were interior to the program, as part of accepting that work with NASA, we were given guaranteed time on this new telescope, especially in the first cycle. And so I knew I had 100 hours of guaranteed time that I was planning to use for solar system observations.
Heidi came to me and she said, I really want my time and my projects to go to the solar system community so that they have this data in hand for future cycles and they really see what we can do with JWST.
We reached out to the community members and asked them, what do you think we should be doing with JWST? What would be unique? What would be challenging? And we invited them to send little tiny mini proposals to me and to my team.
And so we had a couple of conversations about what that program would look like. And she wanted to cover the entire solar system with her time that she was allocated. And so we broke up her time to all of the different planets that we can observe with JWST. So Mars on out, near-Earth asteroids, comets, some of the main features of things like the Great Red Spot, Uranus, Neptune, the outer solar system, all these things. We decided that we needed to have a point person for each of these targets. They would have their own science teams, but we needed somebody to be the go-to that would be responsible for making sure the observations were planned and delivered and the data was published. The best part of Heidi's entire GTO program is it's very international. And that just goes to show how international this project is, how international it is for astronomy, for planetary science. We aren't just one small niche group. We aren't 2 or 3 people sitting in a room that are the experts in the field. It takes a whole team. And a lot of that team comes from many different areas and many different backgrounds even. And all of that helps feed in and provide the information that we need to really get a grip on what this data is telling us, learn something about the solar system or the universe in ways that we haven't been able to do.
So one of the things we had to decide as a science working group was how fast really were we going to try to push JWST. After a lot of dialogue, we decided that the orbit of Mars would be the limiting factor. And we looked at how fast Mars moved in the sky. And we said, okay, so that's going to be our target goal for the moving target tracking. That would then be fast enough that it would allow observations of Saturn and Jupiter and Neptune and the Kuiper Belt objects, which all move slower than Mars. NASA had a mission called the DART mission, the Double Asteroid Redirect Test, where they crashed a spacecraft into the moon of an asteroid, and they were looking to see if they could move that moon. Part of the observing we decided to do was try to use JWST to do that. The challenge was that asteroid system with the moon was actually going 3 times faster than the upper limit we had all agreed to in the development of JWST. Huge thanks to the engineers and the operating team for JWST. They were actually able to get the telescope to track fast enough to do that asteroid test, and we did get some fabulous observations with JWST.
So with Webb, we get to see things that we cannot at the present day see from the Earth. Primarily that's because of the Earth's atmosphere. We cannot see through the Earth's atmosphere at some frequencies of light. So what Webb gives us is the ability to go into space and to look at objects that would otherwise we couldn't see at certain wavelengths. And in particular, that's really important for molecular astronomy, which is what I do, which means that we can see the molecules in the atmosphere, tell us information about what the atmospheric composition, temperature, and winds are doing. And basically we're working as a team and trying to decipher the puzzle of Titan's weather. One of the things that we're looking at right now is some of the surface features. Titan has lakes and seas, which are in its northern hemisphere. These are seas of methane, quite unlike the seas that we see on the Earth, but at the same time with some of the same characteristics in terms of rainfall and rivers and shorelines and this sort of stuff. So we're very excited to look at those and see if they're still the same lakes and seas that were seen by Cassini.
You know, we have a lot of stuff going on Mars. We have orbiters and everything. But James Webb can see Mars from the whole side. You can see the whole side of Mars, and you can map it. And this is something that rarely you can do with an instrument like available on James Webb. And that has been amazing because now we can go and look for molecules like methane, which is natural gas, that it could be an indicator of past biology or current biology. That's why we are excited about it. That's what we are working on right now. The same thing we can apply to Europa and Enceladus. And you know, Enceladus is a relatively small moon compared to Mars, but it's like that, waiting to see a little pixel, you know, and something. And then when we point there, we saw a huge plume there. So I mean, when you see those things that, you know, you really get surprised. This cannot be real. So you go back to the data, and then you confirm that there's a big plume coming out of Enceladus.
Some of the data hasn't come yet. I'm still waiting for the Neptune science data. We have a Neptune image that was taken as part of a program to make some beautiful pictures for press releases. And boy, did that whet my appetite for what we will see with the Neptune science.
Even when we were commissioning the telescope, one of our commissioning projects was to look at Jupiter, just so we could study scattered light across the instruments. And within a single minute worth of looking at Jupiter, we already knew that we could detect the rings, the satellites, the Great Red Spot, the aurora, there's haze layers. We saw all of that with 1 minute in commissioning. Already knew this was going to be a revolutionary telescope.